Good to see you.
You're welcome once again. So we started the discussion on the survival analysis yesterday. And yesterday we were supposed to go through the introduction to survival analysis and life table, using life table approach. Somebody is making noise. I don't know. Everybody should be muted. Who is this person? Okay. So what I'll just quickly do, because of I'll just rush through without wasting time. Let me just rush through, then we'll quickly run. So we'll talk about survival analysis, a statistical technique used to analyze time to event variable. No, time to event. The outcome variable of interest is time to event. Of course, if the outcome variable of interest is time to event, that shows that the event also is very, very important, whether event occur or not, and the time before that event occurs. So the two most important variables are the event and the time before the event occur. And we talk extensively about the why it is special, because we know that time, we cannot have negative. The time to event cannot be negative time, but there are something that makes this type of variable unique. Number one, time to event always have positive, is always positive, and their distribution are usually skewed. It can be skewed to the right, can be skewed to the left. Like for example, if you are assessing relapse in high risk patient, majority of the relapse may occur early, while few, there will be some delay before the other one will occur. That shows that most of the time, most of the time will be around a particular value, while few we have extremely high value. In that case, it will be skewed to the right. High value, extreme value that is positive, higher than the rest, give positive skewness. But in some situations, so if you are studying time to death in a community-based sample, the majority events we are talking of time to death in the community, just among world. You know that initially few people will die, but as they are becoming older and older, more people will be dying later among those groups. So in that case now, it's skew to the right, to the left rather, because majority have higher value, but we have few that have occurred earlier, which are extremely they're different from the majority that are high. So it will be skewed to the left. So whichever way, it makes it difficult for you to use a parametric approach, the convention and normal parametric statistic to analyze that particular data. Then, and apart from that, standard statistical procedure that assume normality distribution do not apply, then non-parametric procedure could be invoked, except that the fact that there are some additional issue, and the additional issue is that the event in some, if the event occur in some, you can know time to the event. But there are some people that they will drop out before the event occur. You will not know when the event now occur. They maybe due to follow up, they drop out from follow up and they relocate whichever way. You cannot follow them up. But when you stop the study also, the people that have not experienced the event, you won't know. You cannot say this is time to defend, but the only thing you know is that that's the last time you talk to them, you saw them. But the event has not occurred. So whichever way, either they drop out or the event has not occurred after the study end, that is censor. That's what called censoring. So that is a form of positive right censoring. You have left censoring also. When some event occur, you don't even know when it occurred. Maybe you are following people up, maybe every 3 months. After 6 months, somebody will not discover that the event has occurred, but you don't know between the last 3 months, you don't know when it actually occurred. That is left censoring. And we can have people also that have that. That would be interval censoring. So I think this part of the uh, video was not off. I think what we should do is just go straight to life table. Let me quickly explain the life table because it was the explanation of the life table and the analysis that were cut off. So some of the explanation of the life table. So there are many. I talk about different methods for survival analysis. We have parametric method and non-parametric. We have already explained that the parametric method is not appropriate, but still you still use the parametric method. There are some parametric method. If they transform the data, like now, the log normal, if you think it's skewed, you transform, you calculate the natural log or exponential. You can do anti-log, exponential, and it will follow a particular distribution, which is still under parametric. We see we have gamma, but we know that when you transform data, the life is not the same. So the interpretation is so difficult. But when you now come to non-parametric, the two major approaches we use that is used globally for survival analysis is they are non-parametric life table, actually also known as actuarial table, and Kaplan Meier product limit approach. We can call it Kaplan Meier approach or product limit approach. So you see that those two popular approaches are non-parametric. Life table, just a table to describe the distribution of type to event variable. The basic idea of the table is to subdivide the period of the observation into smaller intervals. Then the probability from each of the interval are estimated. So, and we talk about the assumption. Well, the assumption also, they are not special assumptions. Those are the assumptions that must be made, for generally for survival analysis. Let's just go straight to the example. We have an example here. A prospective cohort study designed to study time to death involved 20 who are 65 years of age and older. They roll over a 5-year period, our follow-up for 24 years. So you can see the table here. You can see the table here, and this table, the first table, the longer one, is just the one showing the raw data. There are 20 of them, and this first column is the number of the subject, and that is just to identify the subject. There are 20 subjects, number one, number two, 20 participants. Now, the two variables that are very, very important can be gotten to have idea of the two variables. There is not directly like that in the second and third column. The second column shows the year of death. So the year is death. The event of interest is death. It's not, it's not in all survival analysis that the event is death. So it just happened that this one, the event is death. Because the word survivor comes from the origin of this type of analysis, where they use it to analyze death, time to before time until death, before death, among people that were being enrolled into insurance program. So before they could set their premium, they wanted to know the median time before the enrollment and death, and after the enrollment, from the enrollment to death. So that is why they got the name survivor. How many people survive at a particular time? But the method has been used now over the year to to analyze anything. It can be the event, can be conception, can be relapse, and after treatment for a particular disease. It can be anything. So it can even be time before eruption of the tooth among children. It can be even time before puberty. Think of any event that can happen. The time before it, you can use survival analysis. So this second column now talk about year of death. So this one will give you notion that there are 6 people that die, because they just say this one, number 2, that subject number 2 died at 3rd year, number 7 died at 14th year, number 14 died at 1st year, number 16 23rd year, number 18 at 5th year, number 20 at 17th year. Number 3 is just for identification. So these are so we have 6 people that died. The other people, if you look at it on this column, the other people that you didn't identify, they died, they didn't die. But they are able to tell you the year of the last contact. Of course, the people that die, the year they die are the year of the people that didn't die, the year of last contact. There are many things that can happen. You know, the study ended at 20, the 24th year, after 24 years. So you can see it's only 4 people. Is it 4 now? 3 people. Number 1, number 5, and number 11 that stayed to the end. So those are the people that after the study ended, they have not died. But the rest, they didn't die, but they drop out. Summer. So this one drop out at 11 year, 19 year, 13. So we have different years they drop out. Whether they drop out or at the end of the song, they have not experienced the event. So you wouldn't know if they experienced the event or not at any particular time. So in that case, all of them are censored. So whether they drop out or at the end of the something, the study, the event has not occurred to them, they are all censored in the sense that you will not know actually, you cannot know time to event for them. You only know the time you follow them up. You don't know, you cannot call it time that event has happened. You cannot know. But it's possible for some of them that drop out. The event might have happened, but you didn't know. So you see, the two variables there you can deduce from this table now is that the event occur, yes or no. Then the time the event occur, or the time you follow up, the last follow up for each of them. So if you now want to put in on the table now, what will happen is that you just have a column, the time. All this time, as you go to open the data set, you go to see the way we enter it. All of them are entering the same place, the time, either the dead or not, or whichever way. Those two times they are in the same column. You will not separate that this is the time for death, this is just time. But the only thing that will be a second variable that will show whether the event occur or not. These people in the front of these people that die, they die. The other one, they didn't die. That's what will separate you for the time of death from the sensor time. Now, we are using the life table approach. What it does, it's just a crude way. That was the first approach before some intelligent people came with improved approach. But let's first of all look at it. Though many times nobody used the life table again, but let's just look at it. We ran it yesterday. Okay, as you look at it, you see that you will now decide to divide the time from 0, that is from beginning to 24 years. So you have to now divide the time into interval. So that's the first thing you do in life table approach, so that you'll be able to analysis to now group them. Now, if you choose interval of 5, so you can have 5 groups, which is 0 to 4, 5 to 9, 10 to 14, 15 to 19, and 20 to 24. Now, if you want to put it now, for this 0 to 4, you have 20. You see number, you want to know this column, the first column, number alive at the beginning of the interval. At the beginning of the interval. Of course, you know at the beginning, which is 0 of the study, all the 20, the event has not occurred. So all of them are alive. Those are the people that survive. All of them are survived to that time. So even if the event is not death, they still use survive. That is, they are free of the event, meaning they survive that event. So 20 at the beginning. Now, number of death during that interval. From that 0 to 4 years, how many people die? We know that from here, the 3rd year and the 1st year. Can you see? So there are 2 people that die between 0 and 4 years. This 1, this 3. Then the number that are censored. How many? You see, it's only 2 that drop out at that interval. Only this number 8 at 2nd year drop out. So only 1 person. So this one, if you look at it now, how many survive? You remove these 2, 3. These 2 people and the 3 people, 1 person here, making 3 people. They have already their house, either they die or they drop out in this space. So they will not enter year 5. So from year 5 to 9 now, those who enter year 5, from year 5, they are 17. And the 17, in that interval, how many died between 5 and 19 and 9. If you look at it, it's only one person that died between 5 and 9. Yes, it's only one person. Look at it, and it's 5. The person that died at year 5. But how many dropout? It's 2. This one, can you see number 17 and 19 at year 6 and year 9? You drop out. That's what we put it. So if you look at it now, when you move to the next from 10 to 14 year, you remove these 3 people from 17. You know that the one person died and 2 people drop out. What those people that enter are 14. They enter that interval. And how many died? It's only 1. If you look at it, it's only this person that died at year 14. But that's number 7. And how many people drop out? There are 7 of them that drop out. If you look at it, just count from 10 to this one, number 3, number 6, number 12. I say number 6. Yes, number 6, number 13, and number 15. That's 10 to 14. So there are 4 of them that drop out. So when you now move to the next interval, 15 to 19, you see that 5 people are already out from that 14, remain 9. So how many people die in that interval? It's only one person, that the person that died at year 17, number 20. So how many people drop out? There are 3 of them. Just come from 15 to 19. You see this one, number 4, number 10, and number 18, number 9 and 10. So 3 of them, and you see. So the last one from how many people just live over to 20 year 20. If you remove these 3 and 4, 1 and 3, for 9, from 9, it remain 5 people. So that 5 people, one person died. That is number 16. And the remaining 4, one of them, if you look at it, 20 at 20, I think there's one that dropped out at 20 something, 21. Can you see? Then the remaining 3, 24, they are the one that are last. So making 4 interval, that sensor. Because those last 3, they are sensor also, because at the year 24, the event has not occurred. So when the calculation, I will not go get me just okay. I talk about this notation just for us to be able to calculate. We have different columns. What each column means, I think I've explained. Number at risk. Okay, I think it's on the table there. If you look at the same interval, look at the interval I put. We already put number at risk, which we show here. The first, if you look at the first 4 columns, it's the same thing here. You see the first 4 columns. So this first column will be number at risk during interval, which we have already put there. Number of death during the interval, we have already put them there. You know there are 6 people that died. Then lost to follow up, these are the sensor, we have already put them. If you had all these death and sensor, there will be 20. The death are 16, the sensor are death are 6, the sensor are 14, making 20. Now, how do we now calculate the survivor? The receiver has to first of all calculate the average number at risk. We know that this number at risk, but if you want to know averagely how many at risk, the logic behind it is that those ones that are censored, we don't really know. Some of them, they are lost to follow up. It's possible some of them die also, the thing happened, the event happened to them, they didn't know. So it has become 50-50 for all the people that are censored now. It's either there are equal possibility of it for that the event has happened and that is not happened. So the probability that the event happened, but the probability that is not happened is 0.5. So what is now done here is to divide the number that censored in each category into 2. When you divide it, you now remove it. That will show you that they are still at risk. They are no more at risk, rather. So they are not at risk. So you now, the half of it, you now remove it from the what you have here. Can you see? You believe that half of them are at risk, no, these are the total here. Total here. So you divide the sensor by 2 and remove from this number at risk. Can you see here 20 minus half of 1, which is 0.5. So 0.5 minus 20, making 90.5. This one, 17 minus half of 2. Half of 2 is 1. 17 minus 1, 12. Here is 14 minus half of 4, which is 2. 14 minus 2, 12. This is 9 minus half of 3, which is 1.5. 1.5 from 9 is 7.5. This is 5 minus half of 4, which is 5 minus 2, making 3. So now the proportion die will be 1 for each of the, for this level now, 2 die over 19. It gives you this 1 over 16. Give you this 1, this one 1 over, let me use my notation. Let me use this. This is 1 over 12. Give you this 1 over 7.5. Give you this, and 1 over 3. Give you this. So these are the proportion that. Then the proportion that survive now, that have not died, that survive will be 1 minus. If you calculate the proportion that died, so the proportion that didn't die will be 1 minus that. So 1 minus each of them will give you this. And the proportion, then what we are looking at is cumulative survival, in the sense that you have done this one, proportion that survive is proportion that survive at each interval. But you survive at each interval is conditioned on the fact that you have survived in the previous interval. So the survival at interval 1, the first interval is 0.897. There was nothing previous to that first interval. So the survival is still cumulative, there is 0.897, the same thing. But the survival, the proportion that survive at this second interval will be multiplication of this times this. It will give, can you see, 0.897 times the proportion, the survival at that level, to give you this. The next one will be 0.84 times what we have here, it will give you this. Next one will be 0.770 times what we have here, it will give you this. And the last one will be 0.668 times what we have here, it will give you this. So it's the cumulative. The cumulative is the product that you are multiplying is conditional probability. You know when you say probability that B occur, provided A has occurred. That is, it is a person that has survived the previous interval that will survive the other one. So it's not the person that is alive in 2012 that will be alive in 2013. So it's the person that is alive was alive in 2019 that will be alive in 2020. So you being alive in 2020 is conditioned on being alive in 2019. So that's why it's conditional. You keep on multiplying each interval with the new one. So at the end of the day now, the last interval, the probability of survival is 44.6%. That is 0.4 is 0.446, which is 44.6%. Now, it's the same thing. This table is just the same thing. I just remove all those workings. And so I think we just quickly run it now, because this is what let's just rerun the actuarial table, live table. I don't know if anybody has question. Anybody has question? So somebody should run it. Somebody should run it. Who will share? Somebody that shared yesterday. I'll quickly share. Or should I share from here? But I actually want you to share, because you will learn a lot by participating in it. I don't know who is sharing. Nobody to share, yeah? Okay, let me share.
It's the same time to death too, Abi?
Yeah, the same. The time to death. It's the same thing we are just
okay.
So that I will run it.
Give me permission. Let me share.
Okay. Okay, let me allow, okay. Okay, thank you. All right. So please.
Can I share now?
Yes. If you don't understand, you can let me know. Anyway, please don't wait till the end and say that we run it too fast. Please, at a point, if something is not, you don't understand, let us know, please. Because me, I prefer people understanding from first principle. It's not knowing the last thing that matters. It's knowing the first thing, because your knowing the last thing will be contingent on you understanding the first thing. There's no point knowing the last and the foundation. You don't know. If you don't know, if you really want to do it, you won't be able to do it. It is what that you have not known something. So it's better you know the initial thing, you don't even know the later thing. Later, Even the later you can get to know it, or as you are ruminating, you get to understand, rather than knowing something at the end, then at the beginning. So, okay, yeah, that's great.
Can you see my screen?
Yes, I've seen the screen. Everybody has seen. Can you see now? If you look at this way you enter into the, look at that the way we demonstrated there. It's not the same way you enter it if you want to put it in you want to put in SPS in a software. Can you see? This is the serial number. There are 20 of them. Yes, that one is okay. Now, if you look at it, both we have 6 of them that died. The year, the time in year is the time they die. The other people that didn't die, the time you follow them last, you follow them up last is what you put there is the same thing. But the one man differentiate, the computer will differentiate it. What man differentiate the people that die to show that that is the time they died from. The other one is the event. The event is death. And that event, the one that have the event that died, they are marked them 1, the other one 0. I don't know, is there anything difficult in this? Does anybody need you have question concerning it? How to enter it? Because when you are conceptualizing the study yourself, you must know how to enter it. After all, you are not going to be using hand. Because when you are doing the real something, the sample size is very large. It's not something you can even you are organizing with hand, you want to solve with hand. So we usually use manageable sample size for demonstration so that people can understand. But in real life, it's not that, but it's the same principle. So it's just for you. You must know how to enter it. Okay. If there's no question to that effect, okay, go to analyze. So you can see there are 2 variables there, the time to event and the event. So life table, you go to survivor, then life table. Click on it, sir. Now move the time. You see the time is always there because the survivor is about time. So there's nothing like all those other ones. They say variable, dependent variable. This one is time. If you write it, there is time. So event. Now, why did you say death? Is that event can be anything. So that is why it's event. They now want you to define. When you move the event in, define the event. The event, click on 1 because the people that have the event will mark them 1. Whatever you mark there, you say is the event. You put it continue. But you have skipped something. Continue. You will skip something. When you put the time, you know it's life table you want to do. You want to divide the time into interval. They will tell you 0 through what? You now put the last time there, which is 24. Put 24 there. Then you want to divide it by 5. Interval of 5. Your interval will be 5. 5 years. Thank you. Click OK. So you share. Stop sharing and share the result with us. Share the output. Stop sharing this one and share the output. Are you sharing? Dr. Babagana, I think we have started the place where you missed, right? Dr.
Yes, that's right, sir. We follow it, sir.
Okay, that's great. That's great.
Thank you, sir.
Okay, welcome. The engine is slow. It's coming up over here. That's great. Can we see the result now? You can see. If you see the first column is our first column, interval of time.
I think I'm sharing the wrong.
No, I've seen it. It's the same thing now.
I'm coming. Sorry, just a minute.
It's the same result now.
Okay. You know, because I'm coming.
It's the same result. So
okay.
You see the interval, the first column is our first column in the calculation table also. But the only thing that instead of saying is you use the first time. interval start time. They use start time. The time. You know, this one start from 0 to 4. This one start from 5 to 9. 5 to 9. This one 10 to 14. What is this thing? 10 to 14. This one 15 to 19. And the other one is 20 to 24. So that is the same interval. If you remember the number of people entering the interval, what we got 2017, 14, 9, 5 is the same thing. Then the number withdrawing during interval, that is they're talking of the sensor now. So we do our sensor at the interval. This 1, 2, 3, it's the same thing. Then the number that this column, the number that die, number terminal event is here. Of terminal event is here. You know, there are 6 that die. That's what we have on the table. Then the number exposed at risk we calculated 19.5, 16, 12, 7.53. Then the proportion termination, the proportion that die. When we put this over this is what we give you. It's only in our calculation you shift to about 3 decimal places. They did round it up to 1 decimal place, 2 decimal places here. Then the proportion surviving, it was 1 minus this. If you look at it, the same thing. Then cumulative proportion surviving, the one we did, that was what we got. If you remember, the last one was 0.045, where we say, no, wait, I'm seeing something here. Oh, I'm looking at probability. The probability, this, sorry, 0.446. Yes, 446. You know, if you remember, 446, they already ran their own to 0.45. So it's the same thing. So that is how to do it. It's very simple. So what he give you now, he give you at each interval the cumulative probability. So if somebody survive up to between 9 to 14, between 20, I've shifted that something, 20 to 24, it will give you the cumulative probability of survivor is 45%. That's what it means. Okay, any question? Dr. Ekobo, do you understand this one now? This one. Please, I won't respond. And that's why, you know, I usually ask questions as I'm going. I don't want a situation where we are finished.
Yes, sir. I understand, sir.
Any other person that doesn't understand this, if you have question on this live table now, we are finished with live table. That's how to run it. So this one just give you the standard error, whatever, all those things, but the result you're looking for is this. This is now cumulative probability surviving at the end of the interval. Okay, you can stop sharing, sir. Stop sharing. Let me go straight. Now, we are done with live table. Now, you will see that this live table, if somebody, imagine we arrange in another way, you can decide to say the interval should be 3 years. In that case, you may have about 8 classes, or for 4 years. You can decide to say 7 years or 8 years. So if the interval differ, the probability for each of the interval will be different from what you have gotten now. So what you get at a particular interval is a function of how you range it. So there's no standardized way to do it. Now, people like Edward Kaplan and Meier in 1958.
Sir.
Yes.
Excuse me, sir.
Go on.
Sir, but if the range of intervals differ, the probability in those intervals will be different. But what about the final probability? You know, in time, that timetable, that life table, the last probability we have is a cumulative probability. Are we not going to get the same thing?
You know, because the interval is different. Because the other one is the last for the cumulative up to the last 5 years. It's still a range within the last 5 years. Yes,
okay, so that means if we change the interval,
it will
the
change.
probability we'll get will change.
It will change, but it will not be much. Not that it will not be far, but the value will be different.
Okay, sir. Okay, thank you, sir.
So that is the drawback of that life table. So, these intelligent people, Kaplan, Meier, Edward Kaplan, and Paul Meier, okay, why not at every event, once the event happens, you recalculate the probability. So that probability will be the same thing until the next event. Once event happens, you calculate another probability for them. I don't know if each event, once event happens, you calculate new probability. It's just like when you you do a study, the most recent study you'll be quoting, that will be the value. But once another new study comes, more recent, you change to that one. It's the same thing. So what we now did now is that I talk about the assumption. Then the assumption also is not different from the assumption we have in the generally for survival analysis. I don't want to go to because we discussed it yesterday, but in the life table, look at for the same thing now. What just make life table difference? What I just said. That's all. What make Kaplan Meier different from life table is what I just said. At each point the event have occurred, the survivor is calculated. Look at it. If you now put them 1 to 24, the years now, you put the year. You now put, okay, number at risk at year 0, at 1, 2, 3. If you, okay, you put it. Number at risk, we know that this is number at risk, number of that died, number sensor at each year. So this one look more, it's looking more like the way the raw data is. Now, you want to know, once you first of all put, for you to know number at risk, you have to first of all put, okay, the year, each person, and the year for each year that something happened. Here now, this one is not the serial number, it's the year. You only include the year that something happened anyway. Either there is censorship or there is death. So the year something occurred. Now, you want to calculate the risk. If you want to know the risk, total number at risk. 20 at the beginning, nobody is this is. All of them are at risk. The survivor is, all of them, they are still there. The survivor is 1. So all of them are at risk at 0 at the start, 20 of them, sorry. Then if you now move to year 1, first year, all of them they are at risk. But somebody now died that year 1. Then we now go to year 2. Since somebody has died in year 1, that person did not enter year 2. Can you see? Year 2. So we have only 90 people remaining. Then, but on that year, this year 2, somebody opted out. He didn't opt out. So remaining 18 that enter year 3. Then somebody died in year 3. So when you move to year 5, it remains 17. Somebody died in year 5. When you get to year 6, it remains 16. Somebody opted out in year 6 to year 9, because nothing happened between 6 and 9. That's 7, 8. Nothing happened. So year 9, somebody opted out. Year 14. So when you year 14, it's only year 10 rather. Only 14 enter. Year 11, only 13 enter because somebody opted out in year 14. In year 10, year 12, only 12 because somebody opted out in year 13. In year 11 rather. Now, year 12, somebody opted out. Year 13 remain 11. Like that. Here, it remain 10, it remain 9 here. Because somebody opted out. Here, it remain 7. Because 2 things happened. Somebody died and somebody opted out. 2 of them out of it, they didn't enter year 18. So year 19 remains 6. Year 21, 5, it remain 5. You were 23, it remain 4. You were 24, it remain 3. You remember that 3 people have not experienced the event and they did not observe. The only 3 people finished the study. That's 20 at year 24. So if you now want to calculate the survival probability, is very simple. We know that at the outset, at year 0, at the beginning, the survival is 100%, is 1. But in the second year now, we know there is a cumulative survival. You now move that 1 multiplied by the survival at that year 1, which is 1 minus 20 over 20. Can you see? The survival is that because 1 person died, you remove that 1 person, remain 90 over 20. It give you the, but you now multiply by that previous one, it give you 0.95. So when you get to this one now, you carry that 0.95 here to multiply by the survivor in that year, which is 19 minus 0. Nobody died in 19 over 19. It still give you this. You now carry it here. Sorry. Now carry that one here and use it. That's how you do until you will notice something. When you reach a place where nobody died, it's only opting out. It's the same survivor you have seen, where it will give you the same thing. So when you now, until you get to where somebody died, because we already said that it's only when somebody died that the survivor changed. So at a point that somebody experienced the event, you will calculate the survivor will change. So from the last event, the time the last event happened, the survivor will be the same thing until another event happened. Where will the survivor change? That's what happened until you get to the end. So we now see that the cumulative survivor in the last year is 0.507, which is 50.7. If you remember, in the life table method, the last year is not the last survivor, cumulative survivor, is for 5 years period. It's an interval something. Whereas this one is for that year, a point. So you can see that this one is more accurate. That's why that one was 45 for that interval for year 24. You know, if you look at it, it's an average. That would be an average for that interval. So average between 20 to 24 is 45%. So we are talking of this one for 24 year 24. Can you see the survivor is 50.7%? I don't know if there's any question. So we're going to run the same thing using Kaplan Meier approach. You see the result. Any question on the explanation? Okay, if there's no question.
Yeah, okay.
Okay, then you can share the same thing, sir, so that we rerun it using Kaplan Meier.
Has it come up?
It's coming up.
Okay.
Yeah. So let's go to Kaplan Meier now. Let's go analyze. If you notice now, there's no place for you to divide the time into different intervals because it's not live table. So you define the event. One. The event is 1. So where is it not going? Click on it.
Just put it.
It's hanging.
Okay.
Okay, you can stop sharing. Let me share.
Okay, it's common now.
Okay, okay. Just put 1.
Okay, that's common.
And you put 1. Continue. Now you can click on option. Don't click.
Okay.
Because
okay.
Okay, you have done. Don't worry. Show the result. Don't worry. Stop sharing and share the result. Let's see. We'll go back to that one. Stop sharing and share the results. Yes. Yeah, okay. Scroll down. Let's see the. Okay. Can you see? Let's see the beginning of the table so that we can. Let's see. Scroll down. Scroll up so that we can see that table very well. The whole of that table. Only that table I want us to see. It's okay. It's okay. It's okay. You will see that they listed the time also. The other way we listed, they only listed the time also that something happened. Either somebody died or there is a what do I call it? Censorship. But this is showing the status mean event dead or not. The other one, they are censor. All those zero that they are not no death, no event. You will see. Look at the cumulative for the first year. You know, we know that it didn't show the year zero because we know year zero, that was 1. So if you look at the first year, you will see 0.95. Then if you look at the second year, it's 0.95 also. But it will not tell you because it's 0.95 until the event happened in third year. The event did not happen in second year. Third year, event happened. Now give you a value. Can you see? 0.897 change. So it didn't happen the other year also, it give you another value. But until year 14, no event happen. So this 0.844 is the same. The survivor will be all this year 6, 7, 10. It's the same thing. It's still the same survivor. Until it reaches year 14 where event happen, it change. Calculate the new one. Then year 17 also, new one. Until year 23, it was the same survivor of the year 23, because the year 23 up to year 24, because no event until year 23, up to the end of it is the same survivor, because it's the same thing. Does it make sense? Any question?
Yes, sir.
What's the question? What's the question?
No, I said it makes sense.
Okay. So, Dr. Ikobo, are we okay with the analysis? But that was the part that.
Yes, I'm okay with the analysis.
Okay, that's great. I think you can stop sharing, sir. There's no question from. So that is how to. Oh, I say you should stop sharing. Share again. There's something you miss up. You know, there's something I said yesterday. You know why Kaplan Meier is better than live table is not only because of that thing alone, but you can plot the graph. You can have table and plot the graph. Share again, sir. You can even share the result. Just share that result. From there, we want to go back and plot the table. We want to plot graph. Go to analyze. You are supposed to click on graph the other time. Go to analyze. Okay, before that time, okay, you can go to analyze. Go to analyze. There's something I want to explain when you finish. Survivor. Kaplan Meier. So click on option. So survivor. Want to show survivor graph. Okay, click continue. Click OK. Okay, before we go to the graph, you can see it also shows us the mean, because the screen is not showing us the median, but it's showing us the mean. Can you see the mean survivor time? Okay, let's scroll down on the graph. Scroll down to the graph. Or the graph is in the front? Okay, the graph is okay. Can we see the graph now? So you see the survivor, I said something, look at the graph. You know the survivor is 1 at the beginning now. So any type event happen, it will drop. So in the year 1, it dropped. It will be the same level until when the event happen again. If you look at it, there are 6 deaths. This drop down letter will be 6. 1, 2. This drop down 1, 1, 2, 3, 4, 5, 6. Can you see? There are 6 deaths. Down all these one, this mark, they are the sensor. You know, there are 11 that are sensor because there are 11 that have random sensoring. The remaining 3 is right sensoring, but it's not random. It's field sensor. It's when they were there until the study closed. So this one, if you count that, there will be 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I missed something. You go to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, it should be 10 or 11. But all these marks, that is sensoring. Whenever there's sensoring, we'll mark it. You look at it, even the key here, it says sensoring mark. But when you see ladder drop down, that is when the event, survival function, when the event. So in real life, it's not a curve per se. It's something like step ladder. But theoretically, it's a curve. It's not a smooth curve. That's why when you plot it, it gives you something like this. But of course, if the sample size is very large, it may give the impression that it will be smoother. When you have large sample size, the thing will look smoother than but if the samples are very small, you will see the step. So now, okay, I think we have, as I have explained that. Let's stop sharing. Yes. What is it? Is there any question?
No, I just wanted to just confirm that step.
Hmm?
You know, that step is the death. Because it seems like as if it was at each time there was a loss. That step, you know,
Yes.
that's movement downwards. Does
Yes.
it correlate with the death? That is with
That's the event. That may not have to be death. Yeah, that in this case now is death. It's correlated with the event.
Okay. Because I noticed that one where there was no death was wrong.
Exactly. Will change. It will be horizontal because the survival function, the probability is vertical. The time is horizontal. So from the last death, the survival will remain constant. That's why it's the horizontal until the next death where it will drop. Now,
so the probability will now fall.
Yes.
Okay. Thank you,
Now,
sir. Okay.
You're welcome. Now, this is just showing it. Now, this one is just to show confidence interval. I will not bother with it. It's just sort of regular because all those things computer will give it to you. So you can even ask the computer to show you the confidence interval around the curve. Now, there's something they call cumulative incidence curve. Some researchers prefer to generate cumulative incidence curve as opposed to survival curve, which shows cumulative probability of experiencing the event of interest. So it's not a big deal, it's just 1 minus that survival curve. So cumulative incident or cumulative failure probability is computed as 1 minus the cumulative survivor and can be computed easily from the life table or from the Kaplan Meier also, whatever. Like for example now, look at the same Kaplan Meier we did. This is the last one. This was the what we just finished. This is the cumulative survivor. but just 1 minus this will give you this. Of course, 1 minus 1 here will be 0. 1 minus this will give you this. So the law, you know, because as the time goes on, the survival goes down. So sometimes they want to know the occurrence, that is hazard. They want to see the opposite of the survivor, that is the occurrence now. So the occurrence of the event is going up. The number of events that occur over time is going up. So instead of a graph going down, you want to see a graph going up. That's cumulative failure probability. So I think we can go back and look at it. Will show it's just the opposite to show something like this. I think we should. You can reshare, sir. You can reshare that. Let me stop sharing this. Reshare and let us run in.
Probability of failure. I don't understand that table.
Don't worry. let him share. When you share, we run it that you see. 1 minus the survivor. That's all. 1 minus the survivor, cumulative survivor. You know the cumulative survivor is probability now.
Exactly. Because under the survivor, I saw in that first column, I saw 0.95. And I know that 1 minus 0.95 is not 0.5.
What did you say? There will be 0.005 now.
That last table you showed, I saw 0.005.
Going to be 0.0. When you remove, okay, remove 0.95 from 1. What does it give you? 0.95 from 1.
0.00.
So it will be 0.05 now. 0.05.
I thought I saw 0.5.
And that's what you saw there now. Don't worry, I will go back there. But let him share what he's sharing.
So like you share?
Yes, that's what I said. Share the last one, that last
Okay.
result. That last result. We just want to run something again.
Okay.
Yes. Now, let's go to analyze. Go to the same survivor, Kaplan Meier. Click on the Kaplan Meier. Okay. Go to options. Options. You see 1 minus survivor. The second, click on the second option also. 1 minus survivor. So you go, can you say 1 minus survivor? Continue. Continue.
Yes, sir.
I should leave the other one. Okay.
Yeah, let's leave the other one. So scroll down. Let's see the results. The result will be down now.
Doesn't come out.
Your computer is slow.
Still processing.
The RAM is very small then. Okay, it has come. Scroll down. It has come because you know all those. If you see all those things you have done before. Yes. Can you see? Can you see now? You just put it opposite.
Yes, sir.
And the same thing, if you want to even show the hazard, you know, you were saying you will click the other option. You can click, go there, back there. So it's good to explore all those different possibilities. Go back there and click on hazard also. You're going to see the hazard is, I think it should be the same thing as this 1 minus probability. The way they conceptualize. Let's see. Option. Hazard. Click on hazard. Okay. Continue. Let's see the hazard. You know, what you plotted before was survivor. The hazard now would be the processing. Okay, scroll down. Scroll down. You see?
Yeah.
If you look at it, if they are not different, can you see now? The hazard is opposite. Can you see? If you look at it, can you see it? Do you see? Can you appreciate the difference between the cumulative incident and the hazard? What's the difference? If you look at the table where we calculated it, can we see any difference? If you look at, you can scroll up and down. Let's look at the cumulative 1 minus hazard and 1 minus survivor. Can you see? If you look at the survivor, the hazard now, it goes up more. So
yes, it does. Why?
You know, if you remember, okay, you can stop sharing, sir. Yes, I want to.
You can put up your table.
Yes, I want to show. Yes, I want to show. So what you were saying? Look at the 0.05.
Okay.
So now, what I wanted to show. Okay, I think it's this table. Okay, it's only that we didn't indicate.
Okay, sir, you're not audible, sir. We can't hear you, sir.
What? You cannot hear me?
I can hear him more.
Let me check my volume. My volume is 100%.
We can hear you very well.
Sir.
No, we can hear you.
Well, somebody say cannot.
Very well.
Who cannot hear? Can you hear now? The person that say cannot hear. Who say cannot hear? Maybe it's
even me, I'm back.
It's your network. It's your network, sir.
That's the person.
And you are not in Bonia. You are not in Bonia Island.
No. I'm here in Bayelsa. It was worrying me, but I think
maybe it's your location. Maybe you went to your mansion is in a reserve area for the big men.
So I've been joining. I don't know what went wrong today.
Okay, because if you are far from the mass, from the metropolis, you are in the reserve area where the big people are building big houses. You may not be.
I've been joining.
Okay, now what I want to explain, I want to use just for you to get the idea. Let's use the live table we generated to explain it. It will make more. Is it live table now? Yes. Yeah. If you remember, in this slide, I just want to use as analogy. Though the same thing can happen in the other. If you look at it, first of all, calculate the proportion dying, right? Before we calculated the proportion dying. Before we now remove it from 1 to calculate the surviving. No, after we calculated the surviving, before we calculated the cumulative survivor. So you see, the hazard is the proportion dying. I don't know if you understand me now.
Sorry, sir, I can't hear anything.
Who can somebody hear me?
Yes,
I hear you.
We can hear you.
Somebody say, who cannot hear?
Yeah,
Somebody say cannot. Somebody say cannot hear anything. Who cannot hear anything, please? Maybe who is it, Dr. Ogundeji? Who cannot hear? Please talk.
I can hear you very well.
Who said you could not hear?
I think it's Dr. Bako.
Dr. Bako?
It looks like Dr. Bako.
Okay. Is it Dr. Bako? Can you hear now? He's not responding. Dr. Bako, unless you unmute yourself, you cannot hear. We will not hear you if you talk. Dr. Bako, maybe he has left the place.
It must be network problems. So I've been struggling.
Okay.
between different.
What I was explaining is that the difference between you will be thinking, why can't the hazard function? The hazard be the same thing with the 1 minus survivor. You remember that is 1 minus cumulative survivor. That cumulative incident we plotted, that which is 1 minus survivor, is actually 1 minus cumulative survivor. I don't know if you understand me now. It's 1 minus cumulative survivor. Why the hazard will be the 1 minus survivor itself? I don't know if you get it now. So that was why I want to use the hazard life table to explain it, because on the life table we should calculate the probability dying before proportion surviving, proportion dying, proportion surviving. After proportion surviving, you now do cumulative survivor. And you see, because that cumulative incident we plotted is 1 minus cumulative survivor. It's not just 1 minus survivor. Why the hazard is 1 minus survivor? Can you know the difference? Can you see the difference now? Hazard is 1 minus survivor. Why the cumulative incident is 1 minus cumulative survivor.
Okay. Is that why? That's why it's longer.
The graph differ. Yes. If you look at the graph differ. The hazard function and the cumulative incident, they are different. If you look at it. I don't know if you understand me now. People are not responding. Okay. Okay. So let's talk about comparing.
I hear you, doctor.
Yes. Let's now talk about comparing survival curve. Now, we have plotted the curve now. The curve we plotted using Kaplan Meier or the survivor, just curve is just part of it. It can be presented in a table or curve, Kaplan Meier. Just for one. In a situation you have 2 groups of people or 3 groups, how do you compare them? How do you compare? So there are many tests that people have, you cannot use conventional, we have already established the fact that you cannot use conventional parametric and non-parametric tests to compare the 2 groups. Like now, time before an event, they are skewed. That's one of the reasons you cannot use student t-test. Well, if you cannot use student t-test to compare the 2 times, why can't we use man Whitney? You cannot use it also, because the type of time you have there is not the ordinary time. It's not the time that somebody used to finish a particular procedure, the time of surgery. This one now, because in time of each surgery, at least we are able to. Why is Dr. Balogun? He has not joined. In time of surgery, we are able to collect the information about the time of surgery. But in this time to an event, not all of them, we don't have all the information. Some are censored. I think we have established that fact that some are censored. So because of that, we cannot even use a conventional non-parametric method. So intelligent people also design many tests. The commonest, the most popular one is Lagrange test. It's a popular test to test the null hypothesis of no difference in the survivor between 2 more or more independent groups. What we are saying is that when you have 2 groups now, you plot them. Some of them you may look at it physically physically, by looking at the curve, the graph, and say, oh, this graph is showing that yes, people in the 2 graphs are very close. I don't think they are any different, or they are wide apart, but it's subjective. So how do we quantify that if this survival time for these 2 groups of patient or participant or subject are the same? Non-hypothesis means that there's no difference in their survival time. So we want to test that non-hypothesis. So the test compare the entire survival experience between group and can be thought of as a test of whether the survival curve are identical, overlap or not. If they are identical, they are overlap, they are very good. If the survivor, to be sincere, if no hypothesis is true, you expect the curve to overlap. If they perfectly the same, you won't even see the different color. for the two. Both of them will overlap. Of course, it doesn't have to overlap completely before you say it's the same. If you are very, very close, mean that there's no significant. So the survival curve are estimated for each group, considered separately using the Kaplan Meier method and compared statistically using long-run tests. It is important to know that there are several variations of that long-run test statistics that are implemented by various statistical output computing packages. In fact, you're going to see when we compute it now, the value we compute with had is slightly different from what do I call it? SPSS bring out. Different packages use different, just like you remember when we look at chi-square, we have the same chi-square, we have Pearson, we have likelihood ratio chi-square, because the formula is different. So these values are slightly different when you calculate it. Apart from the fact that when you do your Yates corrected chi-square, to give you different value, all of them, these different value have to do with variation in the formula to arrive at the calculation. It's the same thing. So these Lagrange tests are different versions. Now, a version that is linked closely to the chi-square test statistic compare observed to expected number of events at each time point over the follow-up period. We have an example now. It's the same Kaplan Meier and the same survivor where we're having it for two groups. The one we just finished is for one group. We want to look at two groups now. A clinical trial was run to compare two combination treatment in patients with advanced gastric cancer. 20 participants were stage 4 gastric cancer. With stage 4 gastric cancer, were randomly assigned to receive chemotherapy before surgery or chemotherapy after surgery. The primary outcome is death, and the participants are followed up to 48 hours following enrollment into 48 months, rather, not hours, 48 months. That will be 4 years following enrollment into the trial. If you remember, the cancer is late stage cancer. 6 participants in the chemotherapy before surgery group died over the course of follow-up as compared to 3 participants in the chemotherapy after surgery group. Look at it. The rough presentation. Chemotherapy, this first part of the table, show chemotherapy before surgery, then this one, chemotherapy after surgery. So you can see we have each of the 1, 2, 3, 4, 5, 6, 7, 8, 9, each of them 10, 10. Now, these are the people that die, people that didn't die. They only tell you last contact, you remember. Then for chemotherapy after, these are the people that died, there are people that didn't die. So we have already, the information, we have 6 people died in chemotherapy before surgery, while 3 people died in chemotherapy after surgery. So what they are showing there is their time. You should be familiar with the way they will present, you encounter this type of problem data. Other participants in each group were followed up for varying number of months, some to the end of the study at 48 months, the chemotherapy after surgery group. So you can see that all the remaining 6 people that didn't die in chemotherapy before surgery drop out before 48. Some people drop out here also, but 3 still remain for chemotherapy after surgery. 3 still remain after the follow-up. Now, let's look at the table. We try to calculate with hand before we go into to the calculation. Now, as usual, when you are tabulating the time here, you only show the time something happened. The time you won't say you want to list time. If that's the case, you have to list infinite number of times because there are many times in between that. So it's only the time something happened among So first of all, I have the first table for the first group before surgery. So usually indicates 0 as one of the time. That should to show that you have to show the number that are available at the beginning. So you can see 8 months, 12 months, 14, all those times that something happened. Either somebody die or somebody drop out. Those are the things you show. So you can see, we know that number of deaths. We know that 6 people die in this group, and these are their, of course, their time against their time. Can you see? Now, number sensor. 4 people are sensor. If people die, then 4 people are sensor, and the time also of the sensor. As usual, you want to know the number at risk at time. Is Kaplan Meier table we are using is not live table. Is the live table that you use range of you look for range interval. Well, somebody may ask question. Then if you not have live data, will you be able to use live table? All these exercises are doing for you to understand the logic behind the Kaplan Meier, because it's computer that will run it for you. Even if the data is large, the computer will run within seconds, few minutes or second, it will run it for you. Now, let's just look at it. At the outset, 10 people are at risk because 10 people in this group. At month 8 months, 10 people are still at risk. But out of the 10 people, 1 died. 1 sensor. Can you see? So we are now left with 8 people in the next time, which is 12. Can you see? Because these 2 people are already out. Now, at that month 12 months, 1 died. The 14 month, the next dispensation now, we have 7 people left. In that dispensation, 1 died. The next dispensation, we have 6 people. In that dispensation, 1 drop out. In the next dispensation, we have 5 people. Why I'm saying that dispensation is the next month. It may not be consecutive. It may not be the next month. But the months are listed here anyway. So 1 die here, it remain 4. 1 die, it remain 3. 1 there, it remain 2. 1 drop out, remain 1. That one eventually drop out at 40. So, in this group, they didn't even wait, nothing wait the 48 months. So, if you want to, as we have calculated this Kaplan Meier, look at it, the probability at the inception is 1. So cumulative survivor will be, as we calculated the other time. The same thing do for the other, this is the table for the second one, the chemotherapy after surgery. And that chemotherapy after surgery, you see there are 10 also, but 3 people died. At the inception, 10. At the next distribution, we 25 months. So in their own, nothing even happened until 25 months. 25th month, 2 people drop out. So 20 at the next dispensation, 28 months, you have 8 people entering. 1 die. The next dispensation remains 7. 1 die. Next dispensation remains 6. 1 drop out. Next dispensation remains 5. 1 die. The next dispensation remains 1. And 1 die rather. The next dispensation remains 3. That when they close the study, 3 people waited until they close the study for this chemotherapy after surgery. This is the probability also the survivor. Now, let's move forward. How do you compare? Okay, if you plot it, this is what it will show you. Something like this. We are going to plot it. It will show you 2 Kaplan Meier curve. Chemotherapy before surgery, chemotherapy after surgery. From the look, everybody knows that the deaths were more before surgery because they die earlier. If you look at it, while after surgery they die later. So I even still have some people at the end of the study they have not died. So that is why, can you see? So we have already said, I said yesterday, when the survivor is up, it's not as slanty, it's almost close to being flat, the slope is not much, and it's up there, it doesn't go down. You know that the survivor is better, it's good. When the thing go down sharply and go down, it means it's bad. So we're looking at it, we show you that the survivor is better among the people that receive chemotherapy after surgery and the people that receive chemotherapy before surgery. Now, if you are to put it to test now, you see how further didn't just work like that. After we are done, you have to do further analysis. So what the logic behind the log-rank test now is for you to say, you want to know the expected event, number of events. The event is now is dead. The expected number of events, if actually both of them, the event, because you are testing no hypothesis, and no hypothesis say there's no difference. If there's no difference in the survivor among the two groups, that shows that the event rate is the same. So in that case, you have to calculate the expected number of events in each group if there's no difference in the event rate between the two groups. And we now calculate the actual event. So it's like chi-square. It's actually chi-square. So now we are familiar with observed minus expected. So let's first of all do with the issue of expected before we go to the formula now. Observed minus expected square over observed. That's chi-square. It's purely chi-square. So now this table now, what is showing us is showing us the expected. We are trying to calculate the expected number of events for each group. For this, I'm trying to see, okay. Okay, let's look at the first table. We have listed all the time here that something happened. Then number at risk in group 1, number at risk in group 2. For each of these types, the way we itemize them, number at risk in each type. The only thing there now is that you know that we have missed for the other for the first group, when the event happened was different from when it happened in the second group. But now we have put all the group together now. Now, just like the way we iron them out, the number, if you go and look at the previous table, the number at risk at each group, group 1, group 2, at each time. Then the number of event death in each group, in group 1 and group 2. The number of events. If you remember, in group 1, there are 6 deaths. In group 2, there are 3 deaths. So we are putting again the time the event occurred. Of course, all those other ones, they are censored. If you now see go down now, the number at risk in group 1, just like what I put here, same thing up there. The number at risk in NT, you know, okay, I don't want us to, what I want to also do now, you see the calculation here. You want to see if you want to, here this table is trying to show expected number of events in each group. In each group now, if you have to pull all of
not seeing, I can't see the table.
I
can't see the table. Is it the graph I'm seeing here?
It's not graph. Can somebody see table? Is it that I didn't share this table?
No, it's table we are seeing. We can see table.
We are seeing table, sir.
Graph I'm seeing.
Because it's tables, 2 tables with the lower expected number of events in each group.
Number of events in each group.
Of us to survive today.
No, I'm seeing there are 2 tables there.
I'm seeing table.
Prof is not table.
I'm seeing two tables,
Okay, no
expected
problem.
numbers.
Dr. Ikobo, can you see the table now? Maybe it's your, maybe I think it's your internet. Your internet can lag you behind. Network. It's network. Because the network can lag you behind. Okay. What I was saying, if you look at it, we have already put the number at risk in each group, group 1, group 2. Now the total number at risk for the two groups at each time. Can you see now? We have to add all these two together. So now the number of events in group 1 and group 2, now the total number of events. Can you see now? If you look at that, what we just did is to add this second column and third column to form the total number of events per time for the two groups. Then the event in each group, we add it together to tell you per time the number of events. Then the expected number of events in group 1 now. So in group 1, the expected number of events will now be the number of events in group 1 over, look at it, over the total. You expect that is this event here, the number of events here over the total. The number of events here, sorry, the number of total event here in this one over the total for group 1. You are using this one. You are using to calculate. You still use the total for group 1, but total at risk. But the number of events, because it's assumed that if you are trying to see what will happen if the event is at the same rate. So when I say for expected number of events for group 1 will be, you can actually follow the notation with here. You go to be this, the 10 times OT, which is total, what is the OT here? Total event, can you see? Over total for this one. So you are trying to multiply the number at risk over this over this. It's just like when we are talking of expected row total times column total over grand total. So you are trying to say, okay, the number of events in group 1 should be while the rate in the total times the number contributed by group 1. So that's why you can see OT mean the total event that occur over the grand total, which is this 20 here, times 10, which is the number total at risk at group 1. So when you calculate, it's the same thing we do it for all of them here. I will do for 2 also. If you can follow, I've even explained everything, put the formula also on the heading for you to appreciate. So we will calculate now, for each interval, for each month that something happened, you will see that we calculate the expected number of events for group 1 and group 2. We now add everything together, summation, because for all of them, the summation for here is 2.600 and 20603. Then for group 2 is this. I want you to ask question because it can be tricky. Once though you are not going to be calculated with her just for you to get the logic.
Yes, that notation is not very clear. So the notation is too small for us to appreciate the hand, whatever.
Is it too small?
Yes, too small.
But that is the but I can see if
my own is clear.
Okay. It's clear because the way it's the same thing I'm seeing that you should be seeing.
Mine is very clear, sir.
No, I use glasses.
Mine is clear.
Can you take it again?
Okay, let me take it. Let me take it.
Are you using the phone?
Hey, maximize the screen. Maximize the screen.
No, it's already in the. It's already maximized in the presentation screen. It's on the presentation mode now. So It's already maximized, yes.
But are you using a phone?
Okay.
I'm not using me.
Maximized.
I mean, Dr. Peter, is he using a
Okay,
phone?
okay. Oh, Dr. Peter, are you using phone?
Okay, my computer screen is small. Okay.
That's it.
Which screen? Can you be smaller than my own? Okay, your own is all these 12 inches. Okay, no problem. Or your wife's computer, because it's women computer, usually they put in the bag. That's what you the computer they can put inside bag. Okay, no problem. Let me explain, it will be clear. You will see how you get it is very simple. We have put the time as the first column. The number at risk for group 1 is the second column. That's N1T. N1T. So the number at risk for group 2 is N2T. Now, the total number at risk for the two combined together is just to add the two together. That's what it's equal. We had at each time, we had all the number at risk for each group or the two groups to give you the total. So if there's no group, you didn't divide into group. That's what you get. That's total. If there was ab initio, there was no chemotherapy before chemotherapy, you just lump all of them. This is what you get. This is really the total number because they all what will happen will still happen. You have the total. Then the total, if you see the number of events at each interval for group 1 and group 2, which we have already ironed out, you now added them together to give you the total number of events, which is OT. The total number of events for group 1 is O1T. For group 2 is O2T. The OT means the total number of events. It's just by adding the two together. It's only that all of them happen at different. So if you look at 1 for all this one for this one. So when you add it together, it gives you this. So where you may be having problem is this last two, where you do the calculation. It's very simple. If you are to calculate the rate of event for the total, it will be Q this OT over NT, which is the total number at risk. Is that one clear? If you are to calculate the rate of event for the total without considering any group, it will be OT over NT.
NT, yes, clear.
Yes, which is what is in that bracket in this formula. OT over NT. If you see, it's the same for group 1 and group 2, even in the last two columns. If you look at the bracket, OT over NT, OT over NT. What you just do is that is a proportion of event at each interval generally. So the proportion that will be accrued to each group depends on how many are at risk in each group. That's just to multiply with the number at risk. That's all. It will give you the number of events for each expected number of events at each group. I don't know if you understand now. So when you put OT over NT times, if you want to do it for group 1 now, times
N1T.
the total, yes, N1T.
N1T.
Yes. If you want to do it for group 2, it will be
N2T. 2T.
So these are the expected, that is what you expect rather than what happened. I don't know if you understand that what you expect if there's no difference. That is, you are trying to protect that what happened generally to everybody, that's what has happened now to this group. That's the expected.
Very clear now, sir.
Okay. Is there anybody that is not clear? Any other person? Now.
Thank you, sir.
Yeah. So when you do it for each interval, you add it together, you'll be able to know the total number of expected event for each group, which is what you have here. So when you just come, you remember chi-square now. Chi-square is sigma, sum of observed minus expected square over expected. So for the group 1, the observed, you remember the observed, there are 6 events, number of events here, total here. That's observed. Observed for group 2 is there are 3. Expected for group 1 is 2.62. Expected for group 2, 6.37. Can you see? So it's the same thing. You just say for group 1, 6 observed minus expected 2.6. I just put all the decimal there. Divided by expected plus for the group 2, 3 minus observed minus expected divided square over expected. When you do it, it gives you 6.14808. And the degree of freedom is 1 because it's the number of group minus 1. If you remember, those of you that were in the lecture when we talk about the degree of freedom, even when this last time also I see me mention of it, when I was talking about the understanding statistics beyond the basic concepts. I still talk about the degree of freedom. You know, Dr. Additional has a question one day, say that in short, how do you just describe the degree of freedom? I say the item number of item minus 1. So now depend on the condition. So here now there are 2 groups. So number of group minus 1. So K is number of group. K minus 1. That's 2 minus 1, making degree of 1. I know that the chi-square for the critical value for chi-square degree of 1 is 3.84 at 0.05 level of confidence, level of significance. So because of that now, the value you have calculated is higher. That shows that the p-value will be less than 0.05. So you can say that there's a significant difference in this survivor distribution between the, of course, we look at the graph that even the graph differ, but that one is not quantifiable, but you can quantify it that the difference, we see that the chemotherapy after surgery survive better than the chemotherapy before surgery. So there's a difference in the survivor. Any question? Very simple. So
because the calculated is more than the tabulated.
What did you say?
Is it because the calculated is more than the tabulated? Is that why?
Exactly. Is it just time to talk about reading chi-square from the table?
Okay, the calculated chi-square, right? Are you talking of the chi-square? No, are you talking of the chi-square? Of course, now. In those days when there was no, in those days when there was no computer, nobody can calculate p-value because p-value probability, you cannot calculate it for statistical tests, hypothesis testing. What you can calculate is this from it. So someone like Fisher, intelligent people now draw statistical table to look at it against the critical value. We know that the more the statistic, the less the probability that is due to chance. The higher the statistic, the less the probability that is due to chance. And the less the probability that is due, the better is significant. So most of the statistics move in the direction as the p-value, the probability, except Mark Whitney. You know, we have already said this Mark Whitney and Wilkinson. Those are the only Wilkinson and Mark Whitney. They are the one that move at the, if they increase, the p-value increase also. So the lower the value, the more significant. Those are the exception. Now, here, what we do usually, okay, you look at the critical value. That critical value means that at the corresponding value at 95% confidence level, where the p-value will be 0.05, what will be the critical value, the value of statistics for that degree of freedom? We are saying for 1 degree of freedom is 3.84. So if it's 3.84, when your own calculated value is higher than 3.84, definitely the p-value, corresponding p-value will be less than 0.05. So is it clear now?
Yes, sir.
So it's computer that spoil you people. That's why you find it difficult to understand, because you don't actually need that self. When you run it now, you're going to see the p-value. It will give you the real p-value. You don't need to say, you will know that it's less than 0.05. Okay. I think somebody should share so that we can share chemotherapy 2. The one I sent to you is chemotherapy 2. Who will share chemotherapy 2? Okay, nobody. Okay, some people are shouting. Let me see. I can't hear. Dr. Babagana, can you hear now?
I think it was network at my end.
It was your
yes, so I joined and it picked.
Okay. So please check your system. Okay. Yes, sir. You came late. Welcome, sir.
I don't know, maybe because I've been, yes. having some issues with my internet.
Okay.
When you spoke about comparing two survival curves,
yes,
you said we are going to use log rank test.
Yes.
From what you've done now, you've done the chi-square. Does it mean log rank test for the friend is actually
a chi-square? It's a chi-square. That long rank test is a chi-square.
Okay.
Mm. You know, we have already established the fact that there are many things that follow chi-square. In fact, nobody can know everything. Yeah, a lot of things follow chi-square. A lot of things follow chi-square. There are many tests that the worst statistics, they call it different name. All these Kruka-Wallis is chi-square. Many things follow chi-square. So this one also is a chi-square. Any other one? Okay, who will share chemotherapy too? Okay, somebody, Dr. Gunde is here. That's great. Yes, you will see now. Can everybody see the data set? You will see what makes this one differ. Though it's not the same data set, but what makes this one differ from the other one is that this one, there are two groups. You can see group variable now. Group 1, group 2. Whereas the other one, when we did it, it was the time and event. But this one, group 1, group 2. So those groups, this is what, so you enter them in series, not in parallel. You know, there are two different groups. So when you finish 1 to 10, then 11 to 20 for the other group 2. Start their time and their event. And this time can be time of death or time of sensor, whatever. But what we differentiate, maybe it's time of death or time of sensor, is the event. The one that have 111, those are the ones is time of death you have here. The one that have 0 is time of sensor. Can you see now? So I want to reiterate, because sometimes little you will forget. When you want to run it, you now forget. Oh, you go and put time of event separately, time of death separately, time of sensors separately. No. And when you open your computer, it didn't give you 2 times. It's only 1 time you are entering. So what separates death from sensor is weather event. Just like if they are doing party in one place. Party is party. They now say, is it burial they are doing, or they are doing wedding, or they are doing something else? But the issue is that party, ceremony is ceremony. So other lines is what differentiate the ceremony. Okay, thank you. Let's go. Analyze. Survivor. Survivor Kaplan Meier, yes. You move the time into time, event into status. Define the status first. Define the status, doctor. Yes. Yeah, no, you leave that one, it's okay. If you click on that event, when you just click on event, yes. Yes. Put 1. Well, we enter it as 1. Continue. Yes. The group variable, yes, you are right. Factor. Then don't click to compare factor. Go to compare factor. Log rank test. Continue. Just continue. Then click on options. You want to plug graph. Click survivor. You can click 1 minus survivor also. You know those. Click hazard also if you want. Continue. No, leave those log. This. Okay. So you have to stop sharing and share again. So share again. It's not sharing. Share the result, the output. Okay. Yes, so you can scroll. If you look at it, the table now is showing you all those other one we did. Scroll down. All those other things you did on the table, show you. Then, thank you. Wait, don't rush too much. We know that. Don't rush too much. Let's systematically. You will see the mean of survival time and the median survival time. And you see the mean here, the median on this side. Sometimes for the chemotherapy after surgery, because if you remember, the chemotherapy after surgery is extremely skewed because even at the initial period, nothing happened. Remember. So that's why it's not bringing the median out, but they give the total median. Can you see? Look at the mean, the overall mean, the mean for chemotherapy before surgery and after surgery. You will see that the mean for chemotherapy before surgery is, can you see, is smaller compared 24.5, while the mean for this one 42. Can you see? So it's extremely smaller. So the event occur, people die on time with the chemotherapy before surgery, while people die later or after surgery. And these are just the confidence interval, the mean. We also have the median value and the confidence interval. So now you see this one, the median 26, the year 41, for the total here. You will see something, 26, 46. The mean is smaller than the median. Already is skewed to the left. Can you see? It's skewed to even here. The overall mean is 34, the median. So it's skewed to the left. So we have, what it's telling you is that a lot of things happen initially. It's only few that happen later. That's what it's telling you. Okay. We can look at what we are looking for, log-rank test. You will notice something that the value you get here is 6.1916, but we got 6.1415. So the difference, I've already told you that they have different versions of these long-rank tests, and I've been searching even to actually get the one these people use. The formula for computing exactly. The one, if you use another software, it may be exactly what we calculated. We have different version. Then we are still coming back to run that because there are some other tests also. Best law, you click on it. You know, they also use best law and they have different reasons, but this is the most popular one. And this most popular one, it has different version. Okay, let's scroll down. Let's look at the graph. Let's look at the graph. And look at the survival function. The probability of survival. Of course, it's going down, But if you look at it, the green, it is chemotherapy after surgery. You see that it's high up. And you see, there is only, remember that one was only 3 events. 1, 2, 3. Only 3 events. That's why I dropped down 3 times. And we have a lot of sensors, 1, 2, 3. The remaining 3 sensors, they are terminal, they are field sensor. That's why I put it at the terminal. Can you see? Field sensor. Where the other one are the random sensor. Put those one they'll say at the field, at the end, because 3 live to until they finish the study for group with chemotherapy after surgery. So if you look at this one, there are 6 events. That's why you see 6 drop down. 1, 2, 3, 4, 5, 6. Can you see? 6 events. And the sensor are for 1, 2, 3, 4. Can you see? Sensor are 4. All those mark the sensor. All this list. Yes?
So you mentioned 6 sensor and random sensor.
Yes, I said it yesterday, maybe you forgot. the right sensor that we talk about, the right sensor, there are two types. And the two types also, the first type, type 1, and type 2. Type 1 is divided into fixed and random. In fixed, type 1 right sensor is the sensor at the end that when you finish the study, the one that have not experienced the event and they are still there, they have not dropped out, they ended the study. Of course, they are sensor because you don't still know the time, the event, and you are finished the study. That's when the end of the study, the event has not occurred to them. They are still there. The last time you observed them was the time the study ended. That is fixed type 1 right sensor. Then random type 1 right sensor is this, all those ones that drop out along the way. Along the way, they drop out before the study end. The sensors also, those are random. Those are the ones you are seeing the mark, marking the line. But the fixed one will happen at the end. You will not see it. Then type 2 right sensor is you may decide to say, okay, once certain proportion of the sample size experience the event, you stop the study. That is right sensor also. That one is type 2. Does it make sense?
Yes, sir. Thank you, sir.
Yes, because it's you that determine that one. It's you that fix that one yourself. So that was called specified. You have specified the time. Okay, let's go down to the next.
Yeah, sorry.
Okay, go on.
Okay. Sorry, just maybe it's me that missed it out. Can we go to the raw data? I'm trying to really see, because the serial number was 1 to 20. How are you able to separate 10, 10? Is it that you've been coded for? I just wanted to eyeball it and see.
Okay, no, it's not the person. You can ask the person. Okay, let the person share.
Instead of saying group 1, group 2.
No, group 1 for the first group. Then
group
for
1,
the second
group 1 we coded group 1 for the chemotherapy before surgery, chemotherapy after surgery, group 2. Okay, Doctor Ogudeji, you can start here and share the data editor window, the initial window. Yes, I explained it. Maybe that was when Dr. Balogun was trying to come in. Share the data editor window, that first window before the results.
Okay.
Okay, Dr. Balogun, look at this. You see, the 1 to 10, we mark them, this group, 1111 as their group. Then that's range in number 10. From number 11 to 20 will be the group 2. That's all.
Okay.
And this time,
thank you.
It is their time. It can be time of death or time you last observed. It can be a sensor time or death time. What will separate something is what you need to know, maybe the person died, it's time of death, is the event here. When under the event, the people that die, you mark it 1. The people that don't have the event, 0. That shows that they are sensor. That's all. Okay, go back, sir. Stop sharing this one and now share the result output. That is something we need to explain there.
Thank you.
Now, you can scroll down. One minus, okay. If you remember also, we did the 1 minus survival function. The survival function is a cumulative. It's not just survival at each point. It's cumulative survival. Examiner, it's cumulative. So you now, when you remove 1 minus it, this one also is, they call it incident, cumulative incident. Because if the opposite of survivor is incident now, that is occurrence of the event. So new cases, that is, this one is, every time as people die, they are showing, okay, another one has died, another one, so this is cumulative death accumulating. So it's opposite of, the survivor will be going down, while the rate of death also will be increasing. Because if you are following a cohort, and some people are having the event, and some people, as they are having the event, the person that have not had the event will be knowing that very soon we will have the event also. As more people are having the event, the probability of that remaining person having the event is going higher. Does it make sense? Let's go to the next one. The next graph is the hazard. So what makes this hazard different from the incident is that this one is 1 minus probability of dying. Can you see that? It's different from 1 minus cumulative survivor. For each age, the cumulative survivor we are multiplying by the previous one. But for each point per time, this hazard is not talking about cumulative hazard. Per time, what is the hazard? What the probability of dying per time? Or having the event? It doesn't have to be dead though. What is the probability of having the event per time? That is this one. Okay, there's something. Okay, let's go back, go to analyze. Any question in this area now? Okay, go to analyze. Go back to that place. Meier. Go to that compare factor. Compare factor. Click on compare factor. Up. Yes. Now, you can click on yes, Breslow and Taro Warren. Is it where or where? Continue. Continue. You can click on that option and remove all those. Breslow. You remember now when we did the certified analysis? Remember that Breslow. It's just the same. Yes, those they are the one that different way. It's another way also. All of them also follow the same chi-square anyway. All of them follow chi-square. Different way of just click. Yeah, you can check all this thing. Remove survivor plot. Remove all those plots so that it doesn't bother with the plot. You can even remove all those mean you don't want it to call all those one up. You can remove them so that it doesn't. You just want it to give you only that table. Okay. Yeah, look at it. That's why we have removed all those tables. That's why we don't. So, can you see Lagrange? You can see Breslow, Taro. So, if you look at the value are close also, and if you look at the p-value for the Lagrange 0.09 significant, the other one is 0.06, 0.00. So they are all close. They are all highly significant. It is when something is now close to borderline. If it's around that 0.05 there, you may see that some can manage to be significant, while the other one manage not to be significant. But if you look at it, there is no difference. Okay, what is the difference between 0.05 and 0.06? So that is why sometimes when you want to do regression, anything that has 0.0 something, if it's not up to 1, you tend to include it in your regression. So yesterday we started talking about the life table. We are cementing that. We now talk about Kaplan Meier method. We now see, okay, how do we compare two? That is by using this chi-square. Even if it's still also you compare. You remember chi-square can compare 2, 3, 4 as many groups as possible. Now, the next one, you can stop sharing it, sir. Yes, any question on what we have done? Well understood?
Thank you.
Yeah.
Yes.
Welcome. Okay. So before we round up, let's have a glance about what we're going to be doing. So the remaining thing we want to do now, I want to look at what is hazard ratio, hazard function. We talk about hazard ratio and cost proportional hazard regression. So maybe in the next 30 minutes, few minutes, let's quickly discuss this hazard so that by tomorrow we close, by tomorrow finish up and now run regression. If you look at it now, a very survival analysis is not as difficult. In fact, it's not difficult to run, but you need to understand why people run away or people cannot. Is the fundamental concept, and once you understand the concept, it's very simple. Just like the regression we're going to look at now, it's just like the way you run. Okay, for example, now you can do you can use between male and female chemotherapy, not chemotherapy, and try to see the difference, compare the hazard function. They compare the survival function between male and female, between chemotherapy before surgery, after surgery, between admitted, not admitted. You can use different things to do that. By the time many things are significant, which one is really significant? Where there are some things are confounding for, just like the way you do normal analysis. You see that there are some things are associated. Then, how do you now, since the event is about event happen, did it happen, even though time to the event is there. Other covariates, there are some things that are not categorical. You won't be able to say different group, but they are quantitative, like age, like maybe other function, like the volume of chemotherapy you receive, how frequent is the chemotherapy, all those quantitative variables that may come into play. How are they related? How are they related to that? So just like the way if you want to know something that is either yes or no, so you do logistic, when something is dichotomous, categorical, I now see exposure that is quantitative. Because if the exposure is categorical, you can easily do chi-square to know the association between the categorical exposure and the categorical outcome you have. But when the exposure is quantitative, you can only do logistic regression to know how this exposure that is quantitative determine the outcome that is categorical. But when many people do is that they end up resorting to chi-square by that particular exposure that is quantitative. They now categorize it to make it categorical, and now you chi-square. But whichever way, even if you do that, by the end of if you now see a lot of things that are related, you want to do the regression. So the regression now is to remove confounder. So the type of regression you do depends on the type of outcome. So if your outcome is continuous, you do linear regression. If it's categorical, you do logistic regression. When the outcome is time to an event, when event we are with time to event, we do cost proportional hazard regression. So let's look at this hazard function, proportional. Hazard function is the instantaneous rate at which event occur, given no previous event. Look at the hazard we just plotted. That is, instead of you talking about survive, now you are talking of the event rate itself. So when we talk about hazard function, it's different from the cumulative survival function, because where they differ is that the cumulative try to see what is making noise in the background. Cumulative survival function, look at your survivor, provided you have survived up to that point. Your survivor in 2020, provided you have survived of course, you have to have survived 2019 for you to survive 2020. But the hazard function is talking about the rate of the event at a particular time, irrespective of what has happened. If this person, yes, forget about, you know, the way you conceptualize survival will be different from the way you conceptualize hazard. Because hazard, you cannot say that, so far you have hazard before, you have hazard now. No. Here now, you will not experience any hazard, irrespective of what has happened to anyone. Now, at a particular point in time, what is probability that the event occur? So hazard is instantaneous rate at which event occur, given no previous event. The cumulative hazard describes the accumulative risk up to the time t. So hazard accumulative, the instantaneous hazard function is different from the cumulative hazard. Now, the hazard ratio is defined as the ratio of the hazard function. That is, if you are now dealing with two groups, like the way we just did now, group 1, group 2, we compare the hazard of chemotherapy before surgery by the hazard of chemotherapy among the chemotherapy after surgery. If the hazard among the chemotherapy before surgery is higher, when we divide it by the one that is lower, the other one, it will be greater than 1. If it is lower, the one you put up is lower, and the one you put down, it will be less than 1. Just like odd ratio, dividing odd. So when you divide one hazard among a group by hazard among, that is hazard ratio. Now, the hazard ratio is defined as this and this correspond to the two treatment groups. Typically, we assume proportional hazard. It's a constant function of, is independent of time. What now, in trying to use this hazard function and do cost proportional hazard regression, we are going to talk about it later, the assumption of carrying out cost proportional hazard regression. There must be proportional, that is where the word proportional hazard. Proportional hazard means that per time, it is constant. That is, if in this group, the hazard is 2 times the other group, throughout all the time, along the time, it will be 2 more than. That shows that you expect it to be, even if not parallel, near parallel, but if peradventure you plot the graph, the cross, you cannot hear. Somebody say you cannot hear me. There's nothing wrong with my speaker. Can somebody hear me? People are sleeping.
Yes, I can hear you very well.
Yes, yes, yes.
Anybody can hear me very well.
It must be
it's raining in the place. That place. It's the network. Can you hear now, Hugo?
Okay, I think it's network. Sorry.
It's network, okay.
Thank you, sir.
So I know the reason you cannot hear. It's becoming late. So we'll stop very soon. Yes, it's becoming, that's why you cannot hear. You know, we start by 7, so by 9:30 we should close it. So if you look at these two graphs now, if you plot the hazard, if you look at the hazard function you plotted the other time, hazard over time, of course, you know the hazard goes up now. But peradventure, you now see the hazard cross. Imagine when you do your header, where if the survivor cross, the hazard will cross also. So imagine if you planning the last one with Dr. Ogundeji run. Imagine the two hazard function just cross. You cannot call it proportional hazard. That shows that the relationship between the hazard between the two groups is not constant. It's not proportional, it's not constant throughout. That's why the line cross is called non-proportional hazard. Cost proportional hazard. Okay, maybe before I talk much about that, we can actually run the calculate from what we have done before. It's only that it's not like the hazard ratio here. It's not like odd ratio. When you calculate it, it's not as straightforward as odd ratio or relative risk. It will have been easy without cost proportional hazard. We'll have calculated hazard ratio for that particular one we did. You know, just calculate it on its own. But let's just discuss. Let's not just whet our appetite for that cost proportional hazard. Tomorrow we'll talk about calculating the hazard ratio and the run the cost proportional hazard regression. And just like the way you run simple regression, multiple regression, we're going to run like that. But let me just give some background information to whet our appetite. The cost regression procedure is useful for modeling the time to specify event based upon values of given covariate. You know, the covariates are now other exposure variable that may affect exposure variable that may affect your outcome variable. One or more covariates are used to predict status event. You can predict, like for example now, we know that chemotherapy, the time of chemotherapy can predict whether the person will die on time or not, or the event will occur or not. Sex may be a factor. Other things may be a factor. The time of diagnosis, the stage of the cancer, if it's not the same, the stage of the cancer may be a factor. There are many things that may be a factor that will be covariate. The central statistical attribute is the hazard ratio. Just like odd ratio. And when you do logistic regression, it's odd ratio. So when we do cost proportional hazard regression, it's hazard ratio. The interpretation is also the same. That is Poisson. When we do Poisson regression, it's rate ratio. Remember, rate ratio. The interpretation is the same. In fact, if Dr. MS, when we run the cost proportional hazard regression, we interpret, you see the reason I wanted also, first of all, to go
completely free.
It's okay. Yeah, I honestly, I'll be glad to witness that stage.
Yes, you want to see how the interpretation also almost, in fact, the same like that of Poisson regression, how we interpreted output of Poisson regression. So one or more covariates. So you can mute yourself now. It's like some people are now talking in your background. So data contains sensor and non-sensor cases. You know why you cannot use logistic regression now? That event, no event is because the sensor nature of the data. Similar to logistic regression, but cost proportional as assessing relationship between survival time and covariate. So, assumption made by cost model. Maybe let's just talk about this assumption. Maybe we just stop here. Failure time of individual subjects are independent of each other. You know, when you are trying to, you remember, even in any regression set, it must be independent. That is, the failure time of individual must be independent. You are sure that the data is not from the same, different people with data from different people. Changes in predictor produce proportional change in the hazard regardless of time. Now, what we are now saying is that it must not be this second graph. That's one. So if you try to draw the hazard function, the graph, like we do when Dr. Ogundegi plotted this last one, you see something like this. It's not proportional. a linear association between natural logarithm, relative hazard, and predictor. You know that this one is not a straight line, it's not a linear. You have already seen that we are dealing with skewed data. You can see the type of graph. It's not linear graph. It's not linear. Hazard function or even survival function, they are not linear. So if you want to now use it as a linear, to use a model as a linear relationship between that outcome and covariate, you must transform it. That is why logarithm function is a log of hazard ratio. Just like the way you say log odd. You remember, for linear regression, is original value of y you predict from the value of x. For logistic regression, what you predict is the logarithm of odd, which is logit. And odd is probability over 1 minus probability. And for Poisson regression, is logarithm of the rate, logarithm log lambda, logarithm of the rate. Here is the logarithm of the hazard ratio. So the hazard ratio of two subjects remain the same at all time. Yes, these are assumptions. Explanatory variable acts multiplicatively on the hazard function. I think the same thing with Poisson regression also. The cost proportional hazard model is called semi-parametric model because there are no assumptions about the shape of the baseline hazard function. If you look at it as a thing independent and all those stuff that make it to look like as if it's parametric, it's not parametric, it's semi-parametric. I think let's stop there because I know that I want our brain to be fresh when I want to explain this format. Though we have encountered it before, the time before, but I want us to stop here. If there's any question, tomorrow we'll pick it up. So we know that tomorrow what we are doing is the hazard ratio and cost proportional hazard regression. So any question on what we are doing?
Yeah, not a question, sir. Just to appeal that tomorrow we should start early, 6 o'clock.
No, we are starting early. Sorry for today. It's some exigency here, and it's better. I just feel that instead of me to even shift it by, it's better I just give the time so that instead of saying, okay, even if I'm going to be, I don't want to keep people waiting. I was head somewhere, and that was where I was there when I did the something, you know, did the something and I sent it. And I feel it's better if I say even 6:30 and you are still waiting for me, it will be bad. So tomorrow on Philly is 6 p.m. we start so that we can stop early by 8:30 or 9, latest 9. Yes. Any other?
Because tomorrow NASA is launching people to the International Space Station and I have to be there with them.
Oh, NASA, okay, that's great. That's great. Yeah, you can.
Biden invite you.
So you are no more African Nigeria, you are space Nigeria now.
The Joe Biden invite you.
Let me pause. So,
doing this survival analysis, particularly the Kaplan Meier, and your sample size reduced to a particular level, that you may have to stop the experiment because it will affect the reliability of something like that. I think.
Yes.
I don't know whether
if you look at it, we have already said it now. Normally, when even the sample size for everything, even some people come with the appropriate sample size. You know, apart from generally sample size now for every type of analysis, you come with a formula for sample size. There is even formula I will search that if we can discuss it tomorrow. Sample size for survival analysis, because if the sample size is very small, the power of the study. Look at see now. You look at it. One aspect of for the chemotherapy after surgery, you discover that because the event is not much comparable with the other one, it's only 3, and the other one are sensor. So a lot of dropout. It didn't even show you the median survival time. Can you see that? It didn't show.
Yes.
It didn't show.
Yes.
So when the power is reduced, if the sample size is very small, like any other study, so there's usually minimum sample size. So
Okay.
that's just it.
Okay.
So any other one? Okay, I think we stop.